Good day, everyone. So, let us again discuss a topic in thermodynamic cycles. So, in this video, we will discuss diesel cycle. So, before we proceed to the discussion of the diesel cycle, let us first review again the definition of thermodynamic cycle. So, a thermodynamic cycle is a cyclic process consisting of series of thermodynamic processes which takes place in a certain order in such a way that the final state coincides with the initial state. So the thermodynamic processes are isothermal, which is at constant temperature, isobaric, constant pressure, isochoric, at constant volume, isentropic at constant entropy, and the adiabatic process, which means that delta Q in this process is equal to 0. It means that no heat is added or rejected in the process. So again, this is the PV diagram of the processes. So when you say isochoric, that is constant volume. Adiabatic is this line at constant entropy. Isothermal at constant temperature is at this line. And isobaric is this horizontal line. So last video, we have discussed about Oto cycle. So this is the Oto cycle. So when we say a cycle, the final state coincides with the initial state. So this one is a cycle because at point 1, it goes to point 2 at constant entropy. Then 2 to 3 at constant volume. 3 to 4 at constant entropy. And back to 1 at constant volume process. So this is a cycle. The final state coincides with the initial state. So let us discuss now the diesel cycle. Since I have already discussed this Oto cycle in one of our separate video. So the diesel cycle has these processes. Point 1 to 2, this is a constant pressure process. So Q here, the heat added here from 1 to 2 can be known by using this formula mCp delta T. Then from 2 to 3, the constant entropy process or isentropic expansion. So of course, if that is isentropic, Q is equal to 0. No heat is added or rejected during the process. From 3 to 4, we have constant volume process. So the heat rejected at this process is equal to Q mCb delta T. And the final process is from 4 to 1, back to 1. So that is isentropic compression. Again, when you see isentropic, Q is equal to 0. No heat is added or rejected during the process. Kaya that is equal to 0. So PSB is here means constant pressure, constant entropy, constant volume, and constant entropy process. So here we will discuss what happens during the process. So from 1 to 2, that is the heat addition. So we have here Q added is equal to mCp T2 minus T1 or delta T. And in the process 3 to 4, this is the heat rejection process. So the heat rejected here, QR, is equal to mCb T3 minus T4. So the work done on this cycle happens between 1 to 3. Here we will discuss how to find the efficiency of diesel cycle. So using the first law of thermodynamics, we have here energy in is equal to energy out. So here, as you can see in this diagram, the energy coming into the cycle is QA, or this Q added, and the energy going out of the cycle is work and QR. So QA is equal to work plus QR. Energy in is equal to energy out. QA is equal to work plus QR, or work done is equal to QA minus QR. So That's why we have here work done is equal to heat absorbed QA minus heat rejected QR. So we know that heat absorbed or QA from the previous slide, that is MCP delta T. So we have here MCP T2 minus T1, the final temperature minus the initial temperature. And the heat rejected QR is equal to MCB T3 minus T4. So to find the efficiency, we know that the efficiency is equal to the output, the useful output, divided by the input. So what is the output of this cycle? The output of this cycle is the work done, and the input is the heat absorbed by the cycle or the QA. So knowing that work done is equal to this equation, so we put that here, MCP T2 minus T1 minus MCB T3 minus T4, and the heat absorbed QA, we put it here in the denominator, heat absorbed. So we have here MCP T2 minus T1. Then we simplify this equation. So we divide the numerator by the denominator. So this term here, MCP T2 minus T1 divided by MCP T2 minus T1 is equal to 1. And this another term, negative MCV T3 minus T4 divided by MCP T2 minus T1. Okay, so M will cancel. So we have here CB divided by CP and T3 minus T4 divided by T2 minus T1. That's why we arrive on this equation, 1 minus CB over CP times T3 minus T4 divided by T2 minus T1. Since CP divided by CB is equal to gamma, so this is the specific heat ratio. On other equation, we use K as specific heat ratio, but on this one, we use the Greek letter gamma. So this CB divided by CP here becomes 1 over gamma, because CP over CB is equal to gamma. So that is the reciprocal of the specific heat ratio. Then the general equation is N minus 1 over gamma, or the specific heat ratio, multiplied by T3 minus T4 over T2 minus T1. So from this equation, the general equation of the efficiency, so let us represent temperatures T1, T2, T3 in terms of T4. So here we will convert this T1, T2, and T3 into T4 using the processes. So particularly in this process 4 to 1, we have here isentropic. So that is, if we say isentropic, that is TV raised to y minus 1 or gamma minus 1 is equal to a constant. So in other formula, that is TB raised to K minus 1. But since we are using gamma here, so we have here TB raised to gamma minus 1. So by simplifying, that means T1B1 raised to gamma minus 1 is equal to T4B4 raised to gamma minus 1. So by simplifying the equation, we have T1 over T4 that is equal to the quantity B4 over B1 raised to gamma minus 1. Or simply, because B4 over B1 is the compression ratio R, so we can write this simply as T1 over T4 is equal to R raised to gamma minus 1, or T1 is equal to T4 times R raised to gamma minus 1. So now here we have written the term T1 in terms of T4. So V4 over B1 in thermodynamics, this is the compression ratio. Then we go to process 1 to 2. So for process 1 to 2, we have a constant pressure process. So that means B1 over T1 is equal to B2 over T2. Or at constant pressure process, that is B over T is equal to E constant. So rewriting this one, we have T2 is equal to T1 times B2 divided by B1. So since B2 divided by B1 here, this one, volume of this divided by B1 is equal to the cut-off ratio rho. So we can simply write this one as T2 is equal to T1 times rho. B2 divided by B1 is equal to rho. So that's why we have here T2 is equal to T1 times the cut-off ratio. So but T1 is equal to T4 times R compression ratio raised to gamma minus 1. From this equation, we know this one. Therefore, T2, substitute this T1 here into this equation. So T2 is equal to T1. You replace that T1 by this term. So this becomes T4 times R raised to gamma minus 1 times the cut-off ratio. So we have now written T2 in terms of T4. We have already finished defining the processes 4 to 1, 1 to 2, and now we have here 2 to 3. This is isentropic process still. So from PBT relation, we have again TV raised to gamma minus 1 is equal to a constant. Right? TV raised to gamma minus 1. Or we have here T3 over T2 is equal to B2 divided by B3 raised to gamma minus 1. So B3 divided by B2 here, this is again the expansion ratio here. Right? B3 divided by B2 or B4, since B3 is equal to B4, B4 over B2, we denote this as R1, expansion ratio. So since this is B2 divided by B3, the reciprocal of this one, B3 over B2, then we write the reciprocal 1 over the expansion ratio R1. Then again, 1 over R1 is equal also to rho. Okay, the cut-off ratio divided by the compression ratio. So why is that? So from this equation, we have here R1 B4 over B2, right? If you expand this B4 over B2, this is also equal to B4 divided by B1 multiplied by B1 divided by B2, because B1 here will only cancel. So this expression reduces again to B4 over B2. But B4 over B1, if you remember, B4 divided by B1 is the compression ratio R. And B1 over B2, this is the reciprocal of the cut-off ratio, because cut-off ratio is B2 divided by B1. So this becomes R times 1 over the cut-off ratio, since cut-off ratio is B2 over B1. Or by simplifying further, that is R1, the expansion ratio is equal to the compression ratio divided by the cut-off ratio. So that's why we have here R1. Instead of writing R1 here, we have R over rho. So since R1 is equal to R over rho, then further simplification results to rho divided by R raised to gamma minus 1. So T3 now here, if we simplify, this is equal to T2. You put the T2 here and we copy this expression here. So but again, T2 is equal to T4 times R, the compression ratio raised to gamma minus 1 times the cut-off ratio rho. where do we get this one? This was from previous slide here, from process 1 to 2. Then by substitution, we have now T3. We substitute this value of T2 here. So we copy this expression, T4 times R raised to gamma minus 1 times rho multiplied by this factor, rho divided by R raised to gamma minus 1. So in this next line, this is only simplifying this expression. So we have here T4. This is rho. It is from this row here. So the exponent of that is 1. So by the law of exponent, if we expand this one, that is rho raised to gamma minus 1 divided by R raised to gamma minus 1. So if we combine this row, because of the multiplication, then rho raised to 1 plus, okay, we add the exponent. If you multiply two variable with the same base, you just add the exponent. So this has an exponent of 1, and this has an exponent of gamma minus 1. So you add 1 plus gamma minus 1. Right? So another thing is this one. R raised to gamma minus 1. So if you raise this by the law of exponent to gamma minus 1, then we have here, because this is denominator, this one is from this one. In this factor comes from this one. So this cancels out. R raised to gamma minus 1 divided by R raised to gamma minus 1 is equal to 1. So what we have now is T3 is equal to T4. Then if you simplify the exponent of the cutoff ratio rho, so 1 minus 1 is equal to 0. So ang matitira na lang is gamma. And now we have derived the expression T1, T2, and T3 in terms of T4. So yun ang na-derive natin. So T1 from process 4 to 1, T2 from process 1 to 2, and T3 from process 2 to 3, as we have discussed in the previous slides. So we substitute these values to the original equation of efficiency. Okay, that is 1 minus 1 over gamma multiplied by the expression T3 minus T4 divided by T2 minus T1. So this is only substitution. This will retain. So T3, this one, we write this on this part, minus T4, T2, okay, this whole expression, T4, until here, then minus T1. As you can see, this is the expression written here. Then, again, we simplify this expression. So that is 1 minus 1 over gamma. So collecting the factor T4, we have here T4, right, times rho raised to y minus 1. So that is by factoring this numerator. Then by factoring this in the denominator, we have also T4 as a common factor. So T4 here cancel, because there is a common factor of T4 here and there is a common factor of T4 here. That's why temperature cancels out. So what remains is the factor of this one, rho raised to gamma minus 1. Then also this one here. So what remains is rho times r raised to y minus 1 minus r raised to y minus 1, because T4 will also cancels out. Kasi sabi ko nga, meron tayong common factor na T4 all over the numerator and the denominator. So, matitira na lang dito ay yung rho times r is to gamma minus 1 minus r is to gamma minus 1. So, may common factor na naman tayo dito na r raised to gamma minus 1 here. And the remainder on the other factor will be rho minus, of course, 1. So, common factor naman ito. So, if you distribute this one, and you distribute this to this one, babalik ka dito sa equation na ito. Considering T4 cancels out because sabi ko nga, meron siyang common factor na T4 here, meron siyang common factor na T4 here. So, T4 divided by T4 is equal to 1. Cancels out. So, now, we have the efficiency of diesel 1 minus, you multiply this one to this one, okay, 1 times rho raised to y minus 1 divided by, okay, r raised to gamma minus 1 times gamma times rho minus 1. So, inarrange lang yung dito, mga terms. Okay, so this is now the efficiency of the diesel cycle. So, in other formulas, in diesel cycle, you will see K instead of gamma. Parehas lang naman yan. But basta yung K or gamma is the specific heat ratio, Cp over Cv. This one, Cp over Cv is equal to gamma or the specific heat ratio. So, that is how we derive this efficiency of diesel cycle. But more importantly, other than the efficiency, we have also derived the work done here, knowing T2 and T1 and T3 and T4, knowing the mass, knowing the specific heats and the temperatures at each point 1, 2, 3, and 4. You can compute for the work done. And you can also compute for the heat absorbed. This one, mCp delta T, and the heat rejected, mCb delta T. So, in this discussion, not only efficiency was derived, but also the work, the QA, and the QR. So, hanggang dyan muna. Thank you.